I guess I'll go ahead and get started. So again, good morning. This is day two of the physics camp. I think we should be recording now. Yeah, so this is day two of the physics camp, and yesterday we talked about forces, right? We talked about forces. No, yesterday we talked about vectors. Excuse me. We talked about vectors yesterday. Now vectors have a. Can everybody hear me? Can everybody hear me? I think so. So talk about vectors and how vectors have a certain magnitude and direction associated with them, and how we basically use vectors to kind of describe, certain quantities that we experience in nature. And one of those things is forces. Yesterday we kind of used the example of velocity, acceleration, displacement, uh, things like that are all kind of forces. So kind of following up from yesterday, the application of vectors it's gonna tie directly into how we deal with forces. All right. So today, I'm not gonna do too much, but I really want to kind of just give you a solid foundation of, just what is a force, how we deal with forces. So what is a force? Newton's laws of motion, which you may or may not have heard of. Free body diagrams, which is just it's basically kind of the visual part of dealing with forces, equilibrium, inclined plane, and pulleys. And I have another, section, and I'll get into it if we get there. So, I guess maybe before I tell you what my definition for force is, I kind of want to ask you, what do you think, or how would you define a force? So, if a kid came up to you and asked, what is a force exactly? And you have to define it, with some words. How would you describe it? And kind of while you think about that, I'll go ahead and say that for the most part, um, how you hear force as described in your class is basically a force is a push or a pull. You know, pretty simple definition. Um, yeah, so a force is a push or pull. And I'll also describe it this way, which is, you may not hear it described this way in your class, but depending on how far you go in your physics classes, it may be good to hear this sooner than later. Another way to think of a force is as an interaction. Think of it as an interaction between two objects. Between two objects. All right. So a force is either a push or a pull, or in other words, it's an interaction between two objects, which I think is a good way to kind of think about it. And I kind of have some examples here of some forces that I'm going to be talking about today. So we have something called the normal force, which I'll kind of get more into. The frictional force, which you may already kind of have an idea just by the name of it, what the frictional force is. And the tension force, and weight, which weight is what we call the gravitational force. And these two terms, weight and gravitational force, are very much interchangeable. So just kind of be aware whenever we say weight, we mean the gravitational force. Whenever we say the gravitational force, we mean the weight. And the units for force is named after Isaac Newton, and the units are called newtons. Okay. So let me kind of describe what this normal for, or these forces over here. So these three forces are what we call contact forces. contact forces. Kind of as the name implies, contact forces are forces that are in direct contact with one another. So, I give somebody a high five, our hands, smack each other. That's, obviously a contact force. Then we also have something called long range forces, which is where the gravitational force falls under. So you have long range force. And also, kind of as the name implies, a long range force is a force that happens over a long range. And by long range, basically mean like the two objects are not in contact. So obviously gravity is the obvious example, but another example I kind of want to give is between two magnets. There's some type of force between magnets, right, that repels them away and that also attracts them. But this force is not directly linking them. It's a force they experience, like kind of a field around them. So that's kind of what we call our long range forces. So gravity is also a long range force because the force of gravity comes from Earth, right? The Earth is exerting its gravitational field on us, so things are pulled towards the Earth. But we don't have to be in direct contact with the Earth to, feel this. Basically, which is why objects fall downwards towards the ground, right? Even though this object is not in direct contact with the ground, it's still being pulled towards it. Uh, hey, Elliot, can you hear me?
I'm not sure, but so I can't hear you, but that might just be me. However, they can't seem to see your screen or what you're sharing. So some people say the screen froze. Some people say they see a black screen.
Okay.
Oh, someone says they can hear you though. Yeah, a couple people say they hear you, but there's no screen. So maybe try like refreshing your browser.
Okay.
Or something like that.
Okay. Can everybody hear me now?
I can hear you now, yeah.
Yeah, so everybody can hear me now? Cool. So I'm trying sharing my screen and let me know if you guys can see it. Okay, how's that, Elliot?
I can see it.
Okay, so
check if everyone else can hear it.
Yeah, so yeah, again, can everybody give me a quick yes or no if y'all can hear and see my screen now? Yeah, see both. Yes, yes. Okay, cool. So I'm kind of go back to where I left off, actually.
Yeah, no problem.
So back where I left off at, some people heard me, some people didn't. So, I'm just gonna kind of start back off on what is a force real quickly, right? Those who didn't hear me, we're talking about forces and how yesterday we talked about vectors, and a force is a vector, and basically we define a force as a push or a pull. Defined as a push or a pull. And the units for forces in newtons, as I was saying, and a moment ago I was just describing these four forces here as an example that I'll be kind of talking about today. The normal force, friction, and tension, these are all what we call contact forces because they're in direct contact with whatever they're acting on. And the gravitational force or weight is a long range force. Because it happens at a distance. It doesn't have to be in direct contact with the object to affect it. So contact forces and long-range forces. All right, so kind of moving on in from that. So now we kind of have an idea of what a force is, either through experience or from the definition I just told you, it's either a push or a pull. Okay, we get that. So now I just want to talk about Newton's laws of motion, uh, which basically kind of give us the foundation we need to talk about forces so we can apply them to certain situations. So the first law is, as it states, which may be worded slightly different, depending on your professor or your book, but it usually goes something like this. Newton's first law says that an object at rest, let me underline that, at rest or in motion remains in that state with the same speed and direction unless acted on by an unbalanced force. Right? So this may seem kind of obvious, reading that out loud or hearing me say it. Like of course, something stays at rest or unless it's acted on by force. But I think the a misconception may kind of come in that I want to talk about is with how basically this law is stating that once an object is put into motion by a force, it doesn't necessarily need that force to keep it in motion. So let me kind of write that here. This is basically saying that force, force is what causes an object to move. So force causes object to move. Cause object to move. But it's not needed to keep it in motion. But force is not needed. Force is not needed to keep it in motion. And I'll kind of explain a little further. The force is not needed to keep object in motion. All right. So for each kind of law, I have a visual representation in my mind to kind of help me remember it. And so the one I kind of want to tell you that I keep in mind for this one, and this law is also called the law of inertia. It's also aka the law of inertia. Let's see, Inertia. So the first law is also aka the law of inertia. So think of this incline here. So say we have an incline and there's a ball up there. And here's this flat surface, and let's say this flat surface is ice. So that's what these lines are. It's ice down here. Yeah. And so if I were to ask you, you have this ball here, you're holding it there, and you release the ball while it's on this incline, begins to roll down, then it's gonna start to, slide on the ice here in this direction. And then if I ask you, if the ball continues to slide on the ice, how far will it go? Assuming that this ice is, let's say, it stretches for miles and miles and miles, so we can even assume that it's infinite. When would this, ball stop sliding on the ice? And, some of you may think, well, eventually, the ball is going to stop sliding, right? It has to stop at some point. But we kind of know intuitively when something slides on ice, it just kind of glides and slides for a long time until, something stops it or something's in its way, stops it from moving. So this, I guess the question here is, or the question Newton asked himself was, why does the ball continue to move? Why doesn't it come to a stop? And we know for one, it doesn't come to a stop because if we say there's ice, that's kind of assuming that there is no friction. And if there's no friction, there's nothing to slow the ball down, and so it just kind of continues to roll. But again, like what causes it to kind of continue to roll if there's no forces, pushing on it? And that's basically what we call inertia. So inertia is, by definition, an object's resistance to change. An object's resistance so saying you guys can't see me. See what's going on here. Screen's frozen. Okay. Let me stop sharing. I'm gonna share again. Alright, how about that? So let me know if it's still frozen or not. I guess I'll move around a little bit so you can see. So if you can still see, that's great. For those that the screen was frozen, is it still frozen? Just make sure you can see, you can see, you can see. Okay, cool. Thanks, Liz. All right, so basically, I was just talking about Newton's first law, right? And I was describing how it's also called the law of inertia, and how inertia is basically an object's resistance to change. And what I mean by that is, going back to the analogy I was just using, I got this flat surface made out of ice. You can think of it another way. Think of an ice, what do you call it? A hockey puck, right? And you can imagine you hit it with your, I don't know, that stick thing they use in hockey. And you hit it, and of course, when you hit it, that's applying some force, but that force you apply is only momentary. After you hit it, the cup or the puck will continue to slide, slide, slide and slide. And not just slide, but it's going to slide with the same velocity. So like the velocity here is 10, so the velocity here will be 10, velocity here will be 10, so on and so on. It's going to continue to go with that velocity of 10 meters per second. And that's kind of what they mean here by, when they say with the same speed. So it's going to, remain in that motion with the same speed, unless acted on by an unbalanced force. So there has to be, like another person over here with a puck to stop it. Okay, so that's the first law of motion. And it looks like this, if I were to write it out. And I'll explain. So this right here, this symbol means the sum of, if you haven't seen it before, the sum of, and it's a sigma, a Greek symbol, a capital sigma. So if you ever see that sigma or capital sigma, it means the sum of. So the sum of the forces, or you can write it as the force net. You may see it that way, or you may see, yeah, I think that's the only two ways people write it. So force net, force sum, those two notations are interchangeable. But just know that just means you're trying to add up all the forces and it's equal to 0. So this would be the mathematical expression that goes along with the first law. Hope I'm still kind of transmitting clearly here. Okay, so let's move on to second law then. So the second law, it says if a net external force acts on the object, then the object will accelerate. Okay, pretty straightforward. And that's given by this equation here, force equals mass times acceleration. And of course, force is a vector, so I'm putting a little line on the top. So force net is equal to the mass times the acceleration. So for example, real quick, so we have a box here, a box of, let's say the mass is 5 kilograms. And we apply some force here. Apply this force. And the force is, and we kind of remember yesterday how we wrote our forces this way. How they had x and y components. I'm going to basically continue with that same notation because force is also a vector, so we should be able to represent it that same way. Let's say the force is 10, 10, 0. Right, that makes sense because the force is only in the x direction and there's no y direction because it's a straight line to the right. Okay, so what would the acceleration be? And so we first look at the sum of the forces in this direction. And I'm kind of skipping ahead a little bit, but just to kind of apply this equation real quick. And so we're trying to find the acceleration. Acceleration is question mark. So, and I guess I'll say this too. If we look at this equation, this is basically like two equations in one, kind of, depending on your problem. So, kind of what I mean by that is force is a vector, acceleration is a vector, and we know those vectors have x and y components. So this F equals ma equation kind of splits into two equations. So we have force net in the x direction equal to the mass times the acceleration in the x direction. And then similarly, we have force net in the y direction equals mass times acceleration in the y direction. So just kind of remember, whenever you see, an equation with, vectors, that, those vectors have components, which we can then break into, more equations. Okay, here, the force is in the x direction. So we can spin this on again. Sorry, guys. I wish I knew why I was doing that. Although I know he's talking, I don't see the screen. No worries, guys. I don't know what's going on. I think it's because of the slide deck. The slide deck. I'm not sure what that is. I'm just gonna share it. Let me share it again. PowerPoint? Might be PowerPoint. Sign it back in doesn't help. Okay. I think it's my reception, which is odd because I guess I'm just gonna disconnect and reconnect and refresh my screen. Okay, let me know if you can hear me. I refreshed my screen and reset my Wi-Fi. It looks like I got all my bars now. Okay. Thanks guys for keeping me updated. Let's see. Reception should be a bit better now. Yeah, okay. Alright. So I'm dive right back in then. If it happens again, just let me know and I'll try to refresh it again. So in case this froze, I was just kind of elaborating a little bit, but basically we're talking about Newton's second law still, and so we're talking about Newton's second law, which is given by this equation here at the top, F equals ma. And I was saying how since those are vectors, it that equation can break into two equations. Right, and real quick, I was given this example of a box with a force acting on it, a force of 10 newtons, let's say. And let's say the mass is 5 kilograms. So we want to solve for the acceleration, so we can kind of immediately jump to this equation here and kind of rearrange it with algebra and say, well, acceleration then must be F divided by m. So the force is 10 newtons, so we have 10 divided by 5. So the acceleration then must be 2 meters per second squared. Okay, that's it. So just kind of a real quick example of how we use that equation. It's not typically going to be that straightforward, but sometimes it will be, just to kind of show you how we use that equation. All right, so next then, moving on, the third law, which is one you may have heard in kind of everyday life in all kind of ways. But third law basically says every action has an equal and opposite reaction. Or in other words, if object A exerts a force on object B, then object B exerts an equal opposite force. Let me put that in there. An equal but opposite. And that may sound like an oxymoron, but I'll explain. So then object B exerts an equal but opposite force on object A. So kind of what we mean by that is let's say you have a soccer ball, right? I think soccer balls look like that. No, they don't. Let's say you kick it, right, with your foot. So let's say your foot is object A and the ball is object B, and you kick the ball, so there's a force going that way. So force, this is force from A on to B. So this is a little notation that you might see in class AB. It's frozen again. Okay. I know what I'll do. So it's frozen again. Just a bit of okay, so All right, so instead of using Blackboard, just refresh after every slide. What's working, not working on. Stop freezing. Really? That's so odd. Okay, well, I'm gonna just do this. I'm gonna just share the whiteboard, and I'll just uh, write it out here on the whiteboard. So I was talking about the Newton's third law here. You guys can see the whiteboard, right? Cool. Excuse my handwriting. So we're talking about Newton's third law real quick here, and basically again the third law is every action has an equal opposite reaction. And I was drawing out an example here of a soccer ball and a person kicking it, and how if we call the person's foot, which looks like a hockey puck, but this is a person's foot, and call it A, this is the ball, we call it B. And so the person kicks the ball, so there's a force from A on to B, from A from A on B. Okay, and obviously that makes the ball, fly into the goal or whatever. But when the person kicks the ball, he also feels like, you feel it on your foot when you kick a ball. Not necessarily as much as if you were to kick a rock, because a rock is a much more stable object. But you can imagine that this foot is kicking the ball. Can anyone hear anything? Yeah, can everybody hear me? Yeah, you can. But I guess one person cannot. Karina. So I guess she's gonna leave and come back. Okay. Um. So yeah, let me just get right to it then. So basically, the ball is also acting on the foot. So the ball causes a force onto the foot in the opposite direction. So this would be like force B onto A. So this would be force B onto A. So notice that force, AB is equal in magnitude. At least I tried to make them equal in magnitude, meaning that this force is the same length as this force, but they're in opposite directions. So that's what we mean by uh, equal but opposite. And so I guess in terms of math or the equation, this would be the kind of equation equivalent for Newton's third law here. And so basically, force AB is equal to the negative force BA because it's pointing in the opposite direction. All right, so I'm not going to spend too much time on that. But I will recap real quickly here. The first law is this equals 0. It's the law of inertia. Second law, MA. And the third law, AB. Okay. So basically, the first law, again, is the law of inertia, which says objects remain at rest or at a constant velocity unless acted on by an outside force. So this is for balanced forces. Balanced forces. The second law is for, wouldn't it be? Oh, thanks. Typo. That would be BA, right? It should be the other way around. And so the second law is for unbalanced forces. If the forces are unbalanced, then the object will accelerate by this amount here. And the last one is just the law of action and reaction. So those are Newton's three laws there. So now let's now that I've kind of explained those a little bit, let's go ahead and apply these to some examples, which would kind of be the bulk of the camp today, at least kind of what I want it to be. So go ahead and clear this. I have to check my slides. So next. All right, cool. So the next thing I want to talk about then was free body diagrams. Free body diagrams. And again, I am kind of zooming through this pretty fast-ish. Of course, in your courses, you'll be able to spend a lot more time and kind of dive a little bit deeper into all of this diagram. But I really kind of just want to give you the foundation, right? So kind of the next core concept that you deal with is the free body diagram, which is basically how we visually apply forces to objects so that we can apply our Newton's law equations. So the easiest example is just a box. You'll be dealing with a lot of box problems. So we have this box here just sitting on the table. All right, it's not moving. There's nothing special about this situation or anything. And if I were to ask you, what forces are acting on this box, and you may say, you go ahead and kind of think about it for a second. You automatically say, well, of course there's gravity or the gravitational force acting on the box, because that's what causes things to have, weight. But then there's also another force acting on this box, which was one that I mentioned earlier called the normal force, but now I'll kind of explain it a bit more. So now I'm going about drawing the free body diagram to apply the forces. So we usually start with a dot at the center of our object being this box. So we know there's a force pulling straight downwards, which if you're on Earth, that's always going to be the case. It's always going to be the force pulling down. And I'll write it this way: force with a little subscript g to indicate that that's the gravitational force pulling downwards on the box. And I'll also say this: the gravitational force is given by the mass of the object times g, where g here is put these bars on top. And g here is what we call not the gravitational constant, but the acceleration due to gravity. Acceleration due to gravity. And it has a value of, notice it's a vector, so it's negative 9.8. And it's a negative 9.8 because it pulls downwards. So it's negative. It's negative because it pulls downwards. Alright, that makes sense. So the weight then, I guess another word also for force of gravity, which you may also see this in class. You may also see this written as a W for weight. So interchangeable here, Fg or W, force of gravity or weight, that's interchangeable. Okay, so that's pulling downwards, right? And so now I kind of want to explain the normal force in terms of Newton's first law. So again, Newton's first law said that, I said N1, Newton's first law says that force net equals 0, right, for objects at rest. And so this is clearly an object at rest, and so the sum of the forces must be equal to 0. So if I add up all the forces, they should sum up to 0. So there must be more than just one force, right? So this force of gravity must be canceled out by some other force that's causing it to basically stay on the table. And that's what we call our normal force. So upwards is this normal force. So I use F with a capital N. Alright. So the normal force again is a contact force, right? This normal force is a contact force. Specifically, when an object is in contact with a surface, there's going to be some normal force. So now if we go back to Newton's first law, and we think, well, the sum of the forces should be equal to 0 because this object is at rest. Well, so when we say force net, this is kind of where we go to our free body diagram, which this dot with the arrows, with those arrows or vectors, is our free body diagram. And I'll also draw it like this. It doesn't necessarily have to be on the object. A free body diagram can be detached completely from the object. So FG, FN. So when we go to use our Newton's first law, we look at our free body diagram, and when it says force net, it's talking about all the forces we have on this diagram. So it's in the y direction. So force net, right, in the y direction is equal to 0. Alright, so it's equal to, now we just kind of apply all of our forces here. It's just the normal and force of gravity. And their directions definitely matter, right? Because they're vectors, so directions matter. So up is usually the positive direction, down is usually the negative direction. So we have normal force, and it's going to be minus the force of gravity, right? So now we see basically the normal force minus the force of gravity equal to 0. It just gives us this condition that the force of gravity is equal to force. Okay. So I mean, not much to really say there. This just means that, this box is pushing down on the table, and the table is also pushing upwards on the box, and that's what's causing it to be balanced there. All right. So I want to do another example of a free body diagram, just to kind of get the point across. So again, this is the free body diagram, but let's do a different one. I want to show you how tension comes up in a free body diagram. You guys can hear me, right? Okay. Cool. So again, we're still talking about free body diagram. So now I just want to do another free body diagram for this hanging mass. So this is some block hanging from some rope here and attached to a ceiling. Let's say it's a chandelier or something. And again, we want to draw all the forces that are acting on this object here. So immediately, the first force you should always kind of think to apply to your free body diagram is the force due to gravity. And so drawing your free body diagram, again, you can either draw it on the object or you can kind of draw it off to the side, kind of detached. So there's force of gravity pulling downwards is equal to the mass. Force of gravity is mass times gravity. Okay. And so again, this force can't be by itself if this object is at rest, right? There must be another force that counterbalances with the force of gravity so that this mass just hangs there. And that's what we call the force of tension that's in this rope here. So that rope is basically holding that mass up, right? So call that the force of tension. So I'm calling F with the T. Okay. So you may wonder, is there a normal force? If there's not a normal force, why is there not a normal force? And simply there's not a normal force because this box is not in contact with the surface. it's hanging there in the air. So there's no normal force. No normal force. Because the object is not in touch, not in contact with the ground. The object is not in contact with surface. Okay. Okay, cool. So then now, let's say the mass of this block is, let's use 5 kilograms again. I could then ask you, well, if this block has a mass of 10 kilograms, then what is the force of tension inside of this rope? Assuming that this box is in equilibrium, let me say that as well. So whenever we say an object is in equilibrium, it means the sum of the forces are 0. But I'll kind of get more into that too. But we can just start by saying, we do our free body diagram. We can say, well, this object is at rest because it's just hanging there. So we can say, force net with the sum of the forces is equal to 0. So then we go ahead and go into our free body diagram here and add up all these forces. So we have the force of tension Ft, which is upwards, it's going to be minus Fg, the force due to gravity, because gravity is pulling downwards. And again, that's why we have this negative here, because gravity is pulling downwards. So now we could solve the force of tension. So force due to tension is equal to force due to gravity, the mg. And again, g is roughly about 9.8 meters per second squared. So we can go ahead and immediately just kind of plug in our mass and g here, and we could solve for the force of tension in the rope. Okay, again, I think that's pretty straightforward, but just another example of a free body diagram. And this last example I want to give before I move on, I'm not going to spend too much time on it. Let's say you got a picture frame. This picture is, there's a picture hanging up on the wall or something. And I ask you, what's the free body diagram for this picture frame? So what are all the forces acting on this picture frame? So again, if you're working through this with me, first we immediately say that there's a force of gravity pulling downwards. And then there's these 2 strings that the picture is hanging up by here. And so there's 2 tensions. So there's one this way, there's another one this way. Call it tension 1 and tension 2. Okay. And then that would basically be it for our free body diagram for this picture here. Okay. So with that, let me move on to the next thing I want to talk about. Check my slides. Okay. So the next thing I'm going to talk about is equilibrium, which is kind of what we've already been talking about, so it's a good segue into it. So an object at equilibrium. So let me give you some key words here to kind of keep in mind. So most of the time, when you're dealing with forces in this portion of the class, well, usually all the time, the problems are, they're word problems. They give you the problem in a situational form, so you have to read it, and decipher, you know, what you're reading, and somehow apply what you're reading to some equation. So equilibrium is one of those kind of key words that if you see it in a problem at any time, you automatically should think the sum of the forces are going to be equal to 0, or force net is going to be equal to 0. Force net equal to 0. So again, whenever you see equilibrium, think about this. Another keyword that's kind of synonymous with equilibrium, kind of loosely, is if they say an object is at rest, then we can immediately jump to, this here, saying the sum of the forces is equal to 0. And then lastly, the last kind of key word that's synonymous with this is constant velocity. I'll kind of mix that together there. It says constant velocity. So these three kind of, I guess, phrases or words here, if you ever see them in a problem, they basically all tell you to kind of, start off with setting the sum of the forces equal to 0. So I think that's kind of real key because it just helps with word problems. The constant velocity one it's not as obvious to see that, but it may make sense once you kind of get into the class. I'm not going to focus too much on that because it takes a little bit more explaining. But just kind of know if you see any of these phrases, we could jump straight to the sum of the forces equal to 0. All right. So let's get into, a good solid example. No more taking it too easy on you. So let's draw out the situation here. So let's say this is, a scenario where there's 3 dogs. There's a dog over here. I don't know. I guess it's supposed to be a dog. Okay, and this is a top-down view. So there's 3 dogs here. They're each pulling on this rope toy. So this one's pulling that way, this dog's pulling that way, this dog's pulling downwards. Again, this is a top-down view. Or bird's eye view. Right. And I say top-down view because that's going to let us know that we don't have to include the force of gravity. And I'll kind of just let you sit on that. So, yeah, we've got these 3 dogs. Each one of them is pulling on this rope in their, respective directions. So if I were to draw a free body diagram, directly on the center here, now obviously there's going to be a force this way. I'll call it force 3. There's going to be a force this way. I'll call force 1. And down is a force pulling this way. I'll call force 2. Okay. So let's say force 1. We know what force 1 is. Force 1 is given by -2, 0. That's 0. Force 2 is 0, -10. Alright, both of those make sense, right? Because -2, that's basically, to the left, which, lines up with that. 0, -10, goes with this one because it's pointing in the downwards direction. And let's say we don't know what force 3 is. Force 3, question mark. Alright. So force 3 is basically what we want to solve for. We want to find what is force 3. If these 3 dogs are pulling on this toy and we want them to be quote unquote in equilibrium. Basically meaning that as each one of these dogs pull on it, they're not going anywhere. They're just kind of pulling and pulling, but neither one of them is, I guess, winning, quote unquote. So system's in equilibrium. In equilibrium. Okay. So now we say, okay, the system's in equilibrium. We want to solve for force 3, and we know what force 1 and 2 is. All right. And let me go ahead and put a coordinate system down. Let's say that's the y direction. This is the x direction. All right. And force 3 clearly makes an angle. Yeah, there's some angle here for force 3. So what we're going to do is we're going to solve what the vector is for force 3, and we're going to find the magnitude for force 3, and we're going to be able to solve for the angle of force 3. Okay. So now let me kind of show how this connects to yesterday's talk about vectors. So this system's in equilibrium. So we jump straight to saying, well, force net is equal to 0. Okay, cool. So then that breaks into kind of 2 equations, right? We've got the sum forces in the x direction. So we've got forces in the x direction, net equals 0. Forces in the y direction, net also equals 0. Alright. But I guess before breaking it down, we could say that we could also write it this way. Force net equals force 1 plus force 2 plus force 3. All those equal 0. Right, because there's 3 forces, force 1, 2, and 3, acting on this one little toy in the middle, and if we add each one of those up, it should be equal to 0. Right, so force 1, 2, and 3 all add up to 0. So we break it into components. This is kind of how it looks. So for the x, we're only looking at the x components right here. So I'll put in the numbers. So for force 1, it'd be -2. Plus for force 2 is just 0. And we don't know what force 3 is, so let's say plus F3 x component equals 0, right? And so again, I only have 2 here because it's -2. Basically comes from force 1, but it's just the x component for force 1 right here. And so when we get the sum of the forces in the x direction, we only look at the x components for each vector. Similarly, for the y components, it's now be 0 plus -10 plus force 3 in the y direction. All right. And so again, this is similar to kind of what we did yesterday at the very end with the adding up of vectors, right? So when we add up vectors, we just add up their components. So kind of notice how I'm just adding up the x components, I'm adding up these y components, and now we can basically solve for the x component of force 3. All right, we can solve for this x component of force 3. We can solve for this y component. Right. So I think that's pretty straightforward. Solving for f3x, we have a -2 over here, so we can just basically add that over to the right side. So we see that the vector for 3 is going to be 2, 10. Yeah, so 2, 10. So again, just kind of notice how basically I solved for the x and y component. So here is this -10. I added it to the right hand side, solve for the y component. Here is a -2, so I add that to the right hand side to solve for this x component. And so we get that the vector f3, in order for this to be in equilibrium, must be 2, 10. Alright, okay, it's not too bad. So let's go ahead and solve for the angle then, as well as the magnitude. So I'm just going to clear this and rewrite where we left off at. Alright, so at this point now, this is just kind of a recap from yesterday. So now we have the vector of f3 is 2, 10. So we can now solve for the magnitude, which is just going to be the square root of the components, sum of the components squared. And if we put that into our calculator, we basically can solve for what the magnitude is. And then similarly, we could solve for the angle as well, which is going to be our tangent of 10/2. Yeah, 10/2. And we'll be able to solve for the angle. So again, let me draw this picture, how that came together. Right. Cool. So it's force 1, 2, and 3, and we're able to solve for force 3. So force 3 is 2, 10. Its magnitude is so and so. Let's see, 104. Yeah, it's about 10 point something. And the angle here, which I guess probably about 60 something. So we're able to solve for we're able to solve for that force by using Newton's first law. Just summing up the forces and adding them to 0. Okay. So I think that was pretty straightforward. Let me check the PowerPoint. See what I had next. So I had another example of equilibrium. So let's clear that. And I guess I'm trying to focus on examples here because I think that's just the best way to kind of explain these things, because in these examples, certain things come up that you may not have noticed that these equations do initially, right? So I have another example here. All right, so we got basically this box is hanging by these two strings, and let's say this box has a mass of, I don't know, 5 again. Well, let's say 10. Okay, so the box has a mass of 10, and let's say this angle here is 60. All right, so first, we have this picture, and I guess the first thing I would ask you to do is, what's the free body diagram for this ring at the center, and what is the free body diagram of this box down here, this mass here? Alright, so what's the free body diagram for both of those? Because they're going to be separate. Every object has its own free body diagram. Excuse me. If there's more than one object in the problem. And so here, it's kind of like two objects because there's this ring in the center here that's being pulled in 3 different ways by these strings. And then there's this box down here that's been held up by just the string alone. So, use a different color. So starting with this kind of ring in the center, it's supposed to be a ring. I'm gonna draw the free body diagram for that. And we see that there's a tension this way to the left. There's a tension here at some angle, and there's a tension downwards. All right, these are 3 different tensions. So let's name them differently. So this would be 1, this would be 2, 2, this would be 3. Okay, so that's a diagram for the ring at the center, right? So now let's do the free body diagram for this mass at the bottom. It's just a hanging mass, and again, this is in equilibrium, so nothing's moving. Just write UL. Shorthand. So it's in equilibrium. So now see the free body diagram for that hanging mass. So we have a hanging mass. Excuse my lines. So there's a force of gravity pulling straight down on this mass. Force of gravity, so Fg. And then there's a tension upwards. And that tension comes from this string 2, right? So it'd be T2, tension 2 for that. Right? So again, our first step is draw our free body diagram. So we have 2 free body diagrams now, one for the ring at the center and one for this hanging mass here. And I'll say this, we can assume this ring here to be massless. It's just a small ring. And so since that small ring, we're considering to be massless, quote unquote, there's no force of gravity acting on it. So it's just tension downwards. Okay, so now we know the angle and we know the mass. Let's try to solve for each one of these tensions, T1, 2, and 3. Right, so we know that this system's in equilibrium and we want to solve for tension 1, 2, and 3. So let's first look at the mass, the hanging mass here, this free body diagram in red. So for each free body diagram, we basically use Newton's first law. So do the hanging mass all in red. So we have force in the y direction because there's no x direction. Net is equal to 0. So it's equal to, where there's tension upward, so it's T2. There's gravity downward, so minus Fg. Okay, it's not so bad. So we can, immediately just from the hanging mass here, we can solve for what T2 is by using Newton's first law. So T2 equals the force due to gravity. Okay, the force due to gravity, or the weight of the box. The weight of the box, again, is given by mass times gravity. So it's going to be the mass of the box times gravity. And we're G 9.8 meters per second squared. So T2 is going to be 10 times 9.8, so it's 98 newtons. Okay, not so bad then. So we're able to solve for tension 2 just by looking at this red free body diagram from the hanging mass. Alright, so now let's look at this purple free body diagram from the ring at the center. So we know what T2 is. Now I'm just going to solve for T1 and T3. So T3 is the one that's at an angle here. So this is where we kind of apply the knowledge from yesterday. The angle right here. That's our angle there. It's 60. Right, and I'm able to put the angle there, right? Because it's a good question. I was hoping nobody's gonna ask me that. I was thinking about it this whole time. So let me put it like this. The negative in that 9.8, I already kind of took into consideration when I put the negative sign in here for force of gravity. So that was a slight mistake on my part that I was kind of thinking about. So yes, this G is negative. It is negative 9.8, but I kind of already considered it to be negative once I threw that negative in there. Yes, G is 9.8. Yeah. She was asking about, what happened to the negative in the 9.8 that I wrote earlier. And basically I was saying, so G is an acceleration. It's a vector. So let me be slightly more clear here with that. Negative shows the direction. Yeah, exactly. The negative shows the direction, and then G is the magnitude. Nice, you guys good. So this is a vector. And G, that's a vector. So the negative in the G, yeah, basically shows the direction of it. And I guess I should write this like the magnitude of G is just 9.8. And I just kind of considered the negative here already, so I didn't have to say negative 9.8. It's a good call. So we were looking at this angle here for T3 for this third tension, and notice I put the angle down here instead of up here where it was at, and this is just one of those geometrical properties that you've probably seen. I hope you've seen before, at some point somewhere, which basically says like we have these two parallel lines. So like this top line is parallel with, let's say, this orange line here. So this angle on the outside must be the same as this angle here on the inside. Right? Those two angles must be the same. I'm sure you've seen that somewhere before. So in this free body diagram, it just makes it easier to put the angle down here with T3. So it's easier to look at the components, right, of this T3 vector. So this kind of goes back to yesterday when we had these vectors at angles and we were able to look at their x and y components based off of sines and cosines, right? So T3 has a y component as well as an x component, which I'll draw here in a different color, to use red. So there's going to be here this x component, right? So it's like T3 x, and there's the y component over here. It's going upwards, so we have like a T y. Right, it points upwards that way. Okay, that's all fine and dandy. So now let's, and I'll also say this. Yeah, so let's go ahead and do the Newton's first law for this free body diagram in the purple in the x and y direction. So let's start with the y direction. So sum of the forces, or force net, is interchangeable, right? Just to show you both again. So don't be afraid if you see this crazy sigma here. It just means sum of, or the net. Um, so it's equal to 0 because the system is in equilibrium. So now if we look at the y direction of our free body diagram, so we go to our free body diagram here in purple, we look at the y direction, we see obviously there's T2 pulling downwards, but there's also the y component here from tension 3. So this is going to be T3 y, the y component, minus T2. Okay. So now we can, we know what T2 is, it's 98, so we can go ahead and immediately kind of jump in there and solve for that y component of 3. So the y component of 3 is equal to 90, is equal to T2. So it's actually equal to 98. Okay. Newtons. Okay, cool. So now let's do the x direction, alright? So we've done the y direction, now let's do the x direction. We have this, so we can solve for the, let's see. Do we have enough information to solve for that? Well, let's just go anyway. Oh, we do, okay. So now, if you look at the x direction, let me just switch colors. Let's go to orange. Sum of the forces in the x direction equals 0. So if we look at the x direction on our free body diagram here, there's tension 1 to the left, and there's the x component of tension 3 to the right. So T1, let's say to the left is the negative direction. So t3x minus t1. Okay, so now we can set those two equal. So t3x equals t1. Okay. So I think I've left out some information here. Okay, anyway, so I guess I'll kind of end it there anyway. So I think this kind of gets the point across of how we use Newton's first law. That's what time it is. Yeah, because I want to move on to the next part. So let me kind of recap real quick. We have this situation, to give us a picture, and they tell us it's in equilibrium. So immediately we go to drawing our free body diagrams. So kind of getting your picture down, which is always going to be the first step you do. And then in your picture, you want to get all the forces that are acting on the masses or the objects down. So here we have two free body diagrams, one for this center ring and one for the box. And then we apply Newton's first law to both of those. Again, Newton's first law. Then, so we applied that to both of our free body diagrams, and we're able to solve for these tensions. Okay, so now let me move on to the next part, because what does T3x equal? T3x, I guess real quick, is the x component for T3, right? But I think I left out a little bit of information. So just real quick, since you asked, that's T3. T1. Kind of. So when we get the sum of the forces in the x direction, we set that equal to 0. And we ended up seeing that T3x is equal to T1, right? Well, we don't know what T1 is, and we don't know what this x component for T3x is, but we could, yeah, we can break it down in terms of, the angle, which is exactly right, whoever said that there. So T3x, again, looking at this triangle here, T3x is basically equal to the magnitude of T. Let me show you real quick how we do that. So cosine theta, again, just kind of started from scratch, equals T3x over the magnitude of T3. So T3x equals this here, right? So we kind of plug that in up here. Say T3 cosine theta equals T1. But I think I left out something because we know the angle, and I said the angle is 60. So I think we also should, I think I'm missing something. I might have left out some information that we needed. But yeah, so, I mean, you got the right idea though. But let me move on to this next situational problem, which I think is, check this PowerPoint, the inclined plane. The inclined plane. So the inclined plane is another one of those. What am I spelling? So the inclined plane is one of those kind of classic, just physics problems that everyone has to go through and understand. And so I'm going to ask you, find the acceleration. Find acceleration. just gonna say that. So this is our inclined plane here. It's at some angle. And we have a box, excuse me, a box. And there's a box on the incline. So we know if we put some box on an incline, it's gonna slide downwards. So there's gonna be some acceleration in this direction. Alright. So now my question to you is, find the acceleration of this box. And let's say the box has a mass, of 10 kilograms. And let's say the angle is 30 degrees. Okay. So what's going to be the acceleration of this box on this incline? And you say, okay, got this picture, want to find the acceleration. And if the box is accelerating, the forces must be unbalanced, right? So this kind of gets into the second law. So we're going to use the second law, which basically states that the force is equal to mass times acceleration. And we're trying to solve for that acceleration there. Okay, cool. So now we're going to use this here to try to solve that acceleration. So before we kind of apply that equation, we need our free body diagram. So I'm going to draw it directly on the box. And again, it doesn't have to be directly on the box. It just kind of helps sometimes. And so this dot that I'm drawing, I don't think I've mentioned this before, but this dot is supposed to represent that whole mass of the box there, but it's just kind of condensed to a single point. So yeah, there's going to be the force of gravity pulling downwards, right? It's always going to be the first one we draw. And since this box is in contact with the surface, it's going to be a normal force. Now, I didn't mention this before earlier either, but the normal force is always perpendicular. Normal force is always perpendicular to the surface. So what do I mean by that? We'll start here. The normal force is always perpendicular. That's what this symbol here means. This symbol, this upside down T, I guess, is the symbol for perpendicular. Where perpendicular basically means it makes a right angle with the surface. You just kind of think of the fact that this is the right angle. So normal force is always perpendicular with surface. Alright, so notice how like this incline is, it's inclined, it's at an angle. And so the right angle would be like, it's off to the side kind of. It's not directly upwards. It's at this angle because of this incline. Okay. And what else? What are the forces? That's it, right? There's no other forces, just the gravity and then the contact force from gravity, or from the surface, I mean, normal force. So, let me put our coordinate system down. So we got our free body diagram. So another thing we have to do is put our coordinate system. And I know usually we do our coordinate systems like across, right? Just like this I have in the bottom right corner in yellow. Usually we do our coordinate system that way. But for this incline box problem, it's easier to work with this problem if we make our coordinate system slightly tilted, along with the incline. So say this is the x direction, and this here is the y direction. Alright, so just kind of tilt your head a little and you see that this is just our regular coordinate system but slightly tilted so that the x direction is parallel with the incline, right? Now you don't have to do this, but it makes this problem, a 1,000% easier. You could, do this problem with the reference frame right side up. It's still possible. You'll still get the right answer, but at these beginning stages, it's just easier to set it up this way. Okay, so we've got our reference frame, our coordinate system, and our free body diagram on there. So let me draw that again off to the side here, so kind of work in there. Oops, that wrong. There we go. Like that, alright. X and Y direction. This makes a right angle. Alright, so now the last thing I'm gonna put into this free body diagram is the fact that this angle of 30 degrees, this angle of 30 degrees here is the same as this angle here. So this angle that I have in blue, this angle that the force of gravity makes with the y direction, that angle there is the same as this incline angle. You might ask me how or why that's the case. I'm just going to say it's geometry. I could show you, but you could play with it on your own, kind of, and prove to yourself why this angle is the same as this angle in here. So those two angles are the same. It's key to know that. It's really key to know that. Okay, so now we're kind of done now as far as getting our picture down that correctly represents the situation here. And so now let's go about trying to solve for what the acceleration is using Newton's second law. Right. And let me also do this. I'm also going to go ahead and decompose this force of gravity vector. Or basically, I'm going to rewrite it in terms of its components. Because we see that this force of gravity is going to have a y component over here. It's going to have an x component here. So if we look at our free body diagram kind of this way, this here would be the force of gravity x component, right? And then that should be bigger. There's this force of gravity y component. So notice I have this is supposed to be this same free body diagram. The only difference is I have the force of gravity kind of separated into its two vectors. Into its two components, I should say. So we have this x component and this y component here. And we have that angle. Okay, now you might be saying, okay, man, get on with it. It's just kind of really important to have this picture, right? Because that's where, that's how we're going to get to the right answer. So let's go ahead and do Newton's second law, F equals ma for the x and the y direction. So sum of the forces in the x direction, let's start with that, equals the mass times acceleration in the x direction, equals, so looking at the x direction, looking at this x direction here along the plane, the only force that's along the plane there is the x component of gravity. So this x component of gravity is the only thing that's in the x direction. So it's going to be F G x component. Alright. So what is the x component of G going to be? Well, that kind of just goes back to decomposing, is how they say, is decomposing our gravity vector here in x and y components. So let's see what this FGX is. And so you may automatically think, well, the x component goes with cosine, which again is valid most of the time, but here we have to look more closely at this triangle that's being made. So if I take this triangle that's being made right here, I'm going to redraw it. Alright, this down here on the bottom is the y component, that's FGY. This over here is the x component, FGX. And then this up here is the magnitude of FG. Right, so really kind of look at how, this triangle is supposed to be, this triangle just kind of twisted, twisted around. Notice how, I have this adjacent side is the y component, right? So notice that this adjacent side is along the y-axis, right? So that's why the adjacent is y, the opposite of x. Okay, so now we can say, well, using the trig that we know, we see that FGX is going to be FG sine, right? F of GY is going to be FG cosine. Alright. See how I got that, right? Because the y component is the adjacent, and so adjacent goes with cosine, so that's why we have that cosine there. Adjacent over hypotenuse and opposite over hypotenuse for sine. Okay. Cool. So far, so good then. So now, this x component of G, we can go ahead and put it in here for our Newton's second law. Right here, actually. So m, the mass of the block, times acceleration in x direction equals the magnitude of Fg times sine theta, right? Alright, cool. So far, so good. And again, we know that Fg is just mg, right? So Fg is just mg, so let's go ahead and plug that in too. So we got mass times acceleration in x direction, mg sine theta. Alright, cool. Let's cross out. The masses cancel out. Okay, so now we see the acceleration in the x direction, which is along the incline, right? It's equal to g times sine theta. Cool. So we didn't even need the mass. We can solve for the acceleration just by taking acceleration due to gravity, 9.8, and multiplying it by sine of 30 degrees, which is, just to kind of give you the number, it's 4.9. Yeah, because sine of 30 is a half, so yeah. Okay, so that's the inclined plane. And I think, basically the trickiest part about this inclined plane is just this whole free body diagram and, having the angle, just kind of knowing that the angle here of the force of gravity is along the y axis. And then the next step from there is just kind of understanding the trig here. So, um, a lot of first year students miss a step because there's a lot of places where you can miss a step here. Um, so I really kind of want to emphasize this inclined plane, and I want to end it because it's 10:40 now. I don't want to end it now, but I'm gonna do one more example of the inclined plane. Because if you walk through me with that problem and you understand it pretty well, this part of the inclined plane shouldn't be too bad. So now we're gonna have an inclined plane, but we're gonna include friction. So there's gonna be some friction on the incline here. So look at our box. And so now you can imagine if this incline is like sandpaper or something. If it's sandpaper and we have this box on the incline, it may not slide down, right? Because the sandpaper is so rough. Well, basically, there's friction, right? There's friction on the sand. There's friction on the surface. It's causing the box not to slide down, right? So yeah, that's the scenario now. So now let's do the free body diagram. I'll say friction. Okay, so now let's say what is the frictional force that's acting on this box where let's use the same angle of 30 degrees. Yeah, why not? Let's use the same angle of 30 degrees. Let's use the same mass of 10 kilograms. Alright. So now what is the free body diagram? So we've kind of already did the free body diagram kind of a moment ago. Only difference here is gonna be what? And let me also say this. So what force am I missing on that free body diagram? What force am I missing? Kind of while you think about that, I'll also say this is the box is at rest. Friction, yeah, of course, of course. And where do you think it would go on this free body diagram? How would you draw it out? Up left, up left. Cool, cool. And somebody said static friction, which is a very good answer. I didn't even get into the differences between static and you know kinetic friction. Uh, box is at rest is what I was gonna say. So yeah, I think y'all kind of get the idea that the friction is gonna be that way, right? Um, along the incline in this opposite direction. That's going to be the force of friction. This is how I represent that. F with the little subscript F. And again, this notion is all very arbitrary, kind of. You may see the normal force written different. You may see Fg written different. Fg could have been W for the weight, all right? So just kind of know that some people represent these things differently. Alright, some people represent the force of friction with the F, or the normal force with just N, or force of gravity, which is W. Okay, yeah, so for all those who said that, yeah, that's exactly right. So the force of friction is going to be in this opposite direction here. And there's that angle. So the question is, what is the force of friction? Knowing that the box is at rest, that's key. So that's the question, find the force of friction. Okay. And when the box is at rest. So this is slightly different from the last one, right? Only a little bit because the box is at rest. And it's 1047. So the box is at rest. So we could say the sum of the forces is 0, right? That's basically what that statement is telling us. So we can do the sum of the forces in the x and the y direction. So I'm going to write it like this. But let's just look at the x direction. So we got the sum of forces x direction, where again that sigma just means sum of, with the net is equal to 0. So this is equal to 0 because the box is at rest, right? Alright, so it's equal to, let's look at all the forces in the x direction here. Well, we know there's that x component from gravity. So F, G, X, the x component from gravity. And it's going to be minus the frictional force there. Alright. Minus the frictional force. Because it's pointing in the opposite direction. Alright, so that's what we're trying to solve for. We're trying to solve that force of friction. And so we can set it equal to the x component of gravity. And we already know from, a moment ago that the x component of gravity looks like this. Was it sine or cosine? Sine, right? Yeah. So force of gravity sine, and we also could read that this way, mg sine. Alright, so that's our x component. Okay, so we can just set that equal to friction then, because that's what it's telling us right here, that x component is equal to the friction. Alright, so the force of friction is equal to mg sine theta. Alright, so now we could just take that and plug it into we could just plug in our numbers. So we got 10, we got times g times sine of theta. Well, sine of 30 is a half. G is 9.8, so that was the 4.9. So 4.9 times 10, because the mass is 10, you get 49. Okay, so the force of friction on this box is 49 newtons. Alright. Okay, so it is now 10:50. I had a few more examples, like the elevator problem and pulleys that I wanted to get into, but for sure I wanted to get into the incline plane, so as long as we got into this, I think that's fine. Yeah, so let me just kind of recap the important points that I went through today as we wind down. We talked about what is a force. Now, a force is a push or pull or an interaction between objects. We talked about Newton's 3 laws, which are important. So, um, I'll just write them down in their mathematical expressions here. So the first law, which was the law of inertia, said an object will remain at rest or remain in motion unless acted on by an outside object. That's Newton's first law. Newton's second law was force equals ma. So if the forces are unbalanced, uh, this is how they will basically accelerate. And the third law, which I didn't do too many examples of, was every action has an equal but opposite reaction. Right. So I think those are kind of just the key concepts that I talked about today. And then we kind of, we applied Newton's first and second law to a few different situations, just to show us that, yeah, these equations kind of look simple on the surface, but depending on your problem, they can, be more or less elaborate, depending on the problem. What else did I talk about? Objects in equilibrium. So an object's at equilibrium or at rest, that applies to Newton's first law. So, object at rest, equilibrium. Let me just write EUILIBR. I think I spelled that wrong. Close enough. Equilibrium or constant acceleration, constant velocity. So object at rest, object in equilibrium, object with a constant velocity, all those apply to Newton's first law. Newton's second law, unbalanced forces, unbalanced, applies to Newton's second law. And I think that's kind of all I wanted to talk about. That's, the main points I wanted to get across. So again, we see how, dealing with these vectors, we have to, dealing with these forces, we have to understand vectors and how vectors bound into their components, etc., etc. So yeah, I'll leave it at that. Please leave me some feedback. Let me know what you thought. Let me know, was it too easy? Was it too hard? What's the pace? How was the pace? All that. Uh, and tomorrow is going to be the last day of the camps. And tomorrow we'll be talking about equations of motion or kinematics. Um, yeah, so just kind of put it into some context. Day one we talked about vectors. Today we talked about forces, where basically a force is why an object moves. And tomorrow we'll talk about kinematics, which is more so how an object moves. So yeah, it should be interesting. So thanks to everybody being here. Thanks for bearing with me through the technical difficulties. Hopefully that doesn't happen tomorrow. But yeah, you guys have a good morning.